In the next couple of videos, we're going to introduce two key concepts which we need to use to understand vector spaces better. The first of these is linear independence. So here we go. We have to start by defining a linear combination of some vectors in a vector space. If you've got a vector space V, an element v1 up to vn, then a linear combination of v1 up to vn is an element of V of the form a scalar times v1 plus a scalar times v2, and so on up to a scalar times vn. So for example, if your vector space V was r squared, and if you had some vectors, let's say v1 was 1, 1, and v2 was 0, 1, and v3 was equal to minus 1, minus 1, then a linear combination of v1 and v2 and v3 might be, for example, v1 minus 2 v2 plus 3 v3. That is an example of a linear combination of those three vectors. And what is equal to is 1 minus 2 times 0 minus 3 at the top, and 1 minus 2 minus 3 on the bottom, which is minus 2 minus 4. Now, linear combinations actually come up when you're thinking about subspaces, because if you have a subspace U of V, then U must, by definition, be closed under scalar multiplication and closed under addition. So if you use this closure under scalar multiplication and closure under addition properties several times, what you can show is that if you have any collection v1 up to vn of vectors in U, then any linear combination is also in U. So we might say that subspaces are closed under taking linear combinations, and that's just from using the defining properties of closure under addition and scalar multiplication several times. So you noticed here we've used the sigma notation for vectors, just like we use sigma notation in analysis to talk about real numbers. That sigma notation just refers exactly to the expression up here. Now we're ready to define linear independence and linear dependence. Again, let's choose a vector space capital V, and then we say a sequence v1 up to vn of elements of V is linearly independent if the only scalars a1 up to an such that the linear combination a1 v1 plus a2 v2 and so on up to an vn, which is equal to the 0 vector, is the linear combination where all of the scalars are actually 0. We then say that a sequence which is not linearly independent is linearly dependent. And we use abbreviations for this because it gets a bit wordy otherwise. So linearly independent is Li for short, and linearly dependent is Ld for short. So let's look at a couple of examples of this. We will take again V to be the vector space R squared, and we'll take V1 to be the vector 1, 0, and V2 to be the vector 0, 1. We're going to prove that this is linearly independent. So if you want to prove that a sequence of vectors is linearly independent, then you have to show that the only linear combination of those two vectors, which is equal to the 0 vector, is the linear combination where all the scalars were 0. So we should take a linear combination which is equal to the 0 vector and prove that the scalars in that linear combination must all be 0. So let's do this. If a times v1 plus a times v2 is equal to the 0 vector, so here the 0 vector is this, well, a times v1 is a0, and oops, that should be a different scalar, shouldn't it? B. And b times v2 is 0b. So av1 plus bv2 is the vector ab. Okay, but if the vector ab equals the vector 0, 0, then of course a equals 0 and b equals 0. We've shown that the only linear combination of v1 and v2 equal to the 0 vector is the linear combination where both scalars are 0. Therefore, v1 and v2 are linearly independent. On the other hand, if we take a new vector v3 equal to 1, 1, then the sequence v1, v2, v3 is linearly dependent. To show something is linearly dependent, you have to find some scalars, not all 0, such that the linear combination you get using those scalars gives you the 0 vector. That's called a linear dependence relation for v1 and v2 and v3. And actually in this case it's very easy for us just to write one down, because we can prove that these things are linearly dependent by observing that v1 plus v2 minus v3 is equal to 0, 0. So there is a linear combination of v1, v2 and v3. It's 1 times v1 plus 1 times v2 plus minus 1 times v3, which is equal to the 0 vector, and where not all of the scalars are 0. So a bit more terminology. This expression is called a linear dependence relation on the vectors v1, v2, v3. A linear dependence relation is a linear combination which is equal to 0, but in which not all of the scalars are 0. So let me emphasize, if you're trying to find a linear dependence relation for some vectors, if you're trying to prove that they're not linearly independent, so you're trying to prove they're linearly dependent, you need to find a linear combination of those vectors where not all of the scalars are 0, but the linear combination equals the 0 vector. It's okay for some of the scalars to be 0, just not all of them can be 0. Let's look at some more examples. So just for a change, we'll work in c squared, the height 2 column vectors, over the complex numbers. And in fact, what this will really illustrate is it really doesn't make any difference. So we'll take v1 to be 1, 1, and v2 to be 1, minus 1. Those things, I claim, are linearly independent in c squared. So let's prove that. Okay, I want to show they're linearly independent, so I will take a linear combination of v1 and v2 equal to the 0 vector, and I will prove that the scalars in that linear combination must actually both be 0. So if a times v1 plus b times v2 is equal to the 0 vector, then just working out a times v1 plus b times v2, you get a plus b and a minus b equals 0, 0. So a plus b is 0 and a minus b is equal to 0. And of course that's a pair of simultaneous linear equations. It's a system of linear equations in a and b. Even if it was much more complicated than that, you would know how to solve it, because we learned that in the matrices section of 0007. And in this case, we can just solve it in our heads. We get immediately a equals 0, and b equals 0 is the only solution to those equations. That proves linear independence. We showed that the only linear combination of v1 and v2 equal to the 0 vector is the linear combination where both scalars are 0. Okay, next, just an observation. Any sequence containing the 0 vector is linearly dependent. Right, because for example, if your sequence was v1, 0, and then v2, that's linearly dependent as 0 times v1 plus 1 times the 0 vector plus 0 times v2 is equal to the 0 vector. Now again, that genuinely is a linear dependence relation, because not all of the scalars are 0. this scalar is not 0. It's okay that some of the scalars are 0, just so long as not all of them are 0. Alright, so any sequence which contains the 0 vector is linearly dependent. And also any sequence containing the same vector twice is linearly dependent for a similar kind of reason. Like, let's say you had a sequence like V, U, U. It's got the same vector twice in it. Then that is linearly dependent, because if you take 0 times V plus 1 times U plus minus 1 times U, well, that is the 0 vector. And again, this is a linear combination in which not all of the scalars are 0, but which gives you the 0 vector. So V, U, U is linearly dependent. Let's look at some more complex examples of linear independence and linear dependence. We're going to our vector space curly F, consisting of all functions from R to R, with the addition and scalar multiplication defined previously. And we're going to ask about the functions cosine and sine. Those are two functions in F, right? So cosine refers to the function which sends x to cos x, and sine means the function which sends x to sine x. Those are legitimate elements of F. And the question is, are they linearly independent? And the answer is yes. So let's see why that is. Let's give a proof of the linear independence of those functions. So we have to take a linear combination of the cosine and sine function, which is equal to the 0 vector in this vector space, and prove that actually the coefficients in that linear combination must both be 0. So if a times cos plus b times sine is equal to the 0 vector in F, well, let's pause and think what's going on. A and b here are real numbers, they're scalars. Cosine and sine are functions, and the 0 vector, 0 subscript f, is the constant function which is always 0. So a times cosine plus b times sine is always 0. No matter what input you give it, it is always 0. So another way to say this would be to say that a times cos x plus b times sine x is equal to 0 for all real numbers x. So if you choose any particular real number x and substitute it in, then you must get 0. Let's put x equals 0 in there. Cosine 0 is 1, so I get a. Sine 0 is 0. So I get a plus 0 equals 0. Okay, a equals 0. Now it's also true for x equals pi over 2. So let's just spell out what we're doing there. When x is pi over 2, a times cosine pi over 2, which is a times 0, plus b times sine pi over 2, which is b times 1, so a and b are both 0. We've proved that if a linear combination of cosine and sine was the 0 function, then actually both of the coefficients a and b must be 0. So that's a proof of linear independence for those two functions. Finally, I'm going to leave this final example to you. So here we have three vectors in R cubed, 1, 2, 3, 4, 5, 6, and 7, 8, 9. The question is, are they linearly independent? So do there exist scalars a, b, and c, not all 0, such that a times 1, 2, 3 plus b times 4, 5, 6 plus c times 7, 8, 9 is the 0 vector? So if you write that out, what you'll find is that that is a system of linear equations. And you have methods for solving systems of linear equations. So this is a problem which you know how to solve, and I'd like you to have a go at that before the next lecture. I'll tell you the answer at the start of our next video.